Okay, so here is the 100 foot by 100 foot surface from the previous exercise. Like this assignment states, we have to change those dimensions. So now it's going to be 500 feet by 500 feet with an elevation change of 25 feet. So let's go ahead and first do that. So I'm going to take the surface. It's best that you just work with the top surface, not the actual bounding volume that was part of the last assignment as well. You're just worried about this part of it. So I'm going to type bounding box to create my volume. I'll draw a line that is 500 feet. And for now, I'm just going to go ahead and scale it three-dimensionally. So I'm just going to type scale. You could do it two-dimensionally. It doesn't really matter. So this distance now has to be this distance. And using that same logic, instead of whatever its current elevation changes, it now needs to be 25 feet. So I'm going to do the same thing on the type line, V for vertical, draw 25 feet up. So that's right to there. So you can see it's pretty shrunken down, which is going to, again, help you so it's less contours to manipulate. So I'll go ahead and select those, type scale one dimension. Oops, let's make sure I don't select that one in there. So there's the origin. So again, I'm taking this corner all the way down to that one I just redrew. Which is probably, yep, there we go. So now we can see what that surface looks like. It's much more expanded out and it's not as much elevation change, which again, it might look a little weird, but in terms of having to regrade this, it's going to save you a lot of problems. So now that you have your surface regraded, the next thing you have to do is draw your platform. I went ahead and drew it here. So again, it's just 25 by 15. You use this rectangle there. I'm going to just say 25, 50, and there's your platform. You can start to manually move that in Rhino to where you think you want to have it. What's cool is that you can see with that surface there where it starts to intersect with that surface versus when it isn't. So that kind of gives you a preference. But anyway, so let's go into Grasshopper now. So this will see how good my memorization is of that script too. Okay, so what do you think the first thing is that we need to do for the script? Who remembers that first component or first sequence of components? What do I have to do with that platform?
Or a series of points?
I mean, what is the assignment say you have to do to that platform? Slope it down how much? 3%. So that's the first thing you're going to do is actually rotate this rectangle. And the way we're going to set up the script is going to make it so regardless of how you orientate it, it's always going to slope 3% perpendicular instead of 3% along the world axis, which kind of could make it messed up because if you do it, if you rotate it 3% along the world axis, if I have it at this angle, it's still going to rotate it in this direction instead of actually perpendicular to it, which is going to save some irritation. So let's go ahead and take that curve and reference it. The first thing in order to make sure we rotate it on that axis is we have to deconstruct it. So I'm going to go to curve, analysis, and deconstruct rectangle. And you'll see from that, the most important thing is that this plane for that rectangle is always going to be perpendicular to it. So if I rotate this any amount, you can see that that plane follows it. So that's what's going to give us that rotation, that 3% rotation angle, because it's giving us that axis. So let's go ahead and just deselect that. So let's go ahead and rotate at 3%. So if I do rotate, and we're going to use, I think it's rotate 3D. Let's make sure. Yeah, so that's your axis. So the geometry that we're rotating is this curve angle. So this is looking for the angle in radians. So the assignment's asking it for 3%. What I'm going to do first is actually convert it from radians to degrees. So if you just right click on this, you can see there's an option for degrees. This helps us out a little bit. It's still not a percent, but you can go online to figure this out if you're ever given a different percentage. But for now, I'm just going to tell you that 3%, 3% slope conversion to degrees is 1.71. So remember that. But that's obviously not going to be the same value if it's 2% or 5%. You'll have to go online to find that conversion.
That's the conversion
from degrees to percent slope. So that's what 3% looks like in degrees. The center, so we aren't actually going to rotate this from the center. We're actually going to, so instead of taking this flat plane and rotating it from the center point, we're actually going to take that curve and based off of what we've talked about in the grading exercise, we're actually going to rotate it 3% from that point. That again helps with the rest of the script, is that you actually slope it from the high point instead of the center, because then you have to add a couple more operations to figure that out. So what's good is that you can see that the plane starts off at one of those high points, which is nice. So I can take this value and just place it into my C value. So you can start to see it's rotating from that point now, but still rotating in the wrong direction. It's rotating on the XY plane. It's just kind of rotating horizontally instead of vertically. So that's what this next part is. You can see it's asking for that axis. This is something I always kind of have to remind myself on which one's which. You can see that there's a green line there and there's also a red. If I zoom out and look at, let's see if I can find it under the surface. Oops, I probably should show the world axes, the grid axis. We can see that the red is indicating your x-axis and the green is representing your y-axis. So that's good to remember. So let's go back to that. So in order to rotate this in the correct direction, let's lift this up real quick so we can see it. So in order to rotate in the correct direction, we see that the green is actually the axis we want to rotate it off of. So that, again, is your y. So I'm going to plug this into there. Oops. Oh, that's the wrong one. Sorry. So we have to deconstruct this plane real quick. So I'm going to go to vector, deconstruct plane, and that's what's going to break down that plane into the different axes, and that's where you use this y value. And there you go. Now you can see that it's sloping 3% from that point. So we can hide this. We can hide this as well. All right, so we have it sloping in the 3%. The next part is to do what? Let's think about the in-class exercise. Once you've sloped it down 3%, what is the next logical sequence? What else is the assignment asking for you to do with the regrading away from this platform? Yeah. I'd hope you're changing the contours in the grading class. How are you changing them? By what amount? You're sloping your platform 3%, and then what do you have to do to the contours near that platform that you're regrading? What was that, Aaron? Yeah, you have to regrade them out 3-to-1 ratio. But we can't just do it 3-to-1 from all directions, right? We have a low point now that's not at the same value as this one. So this is how we create that trapezoid-like figure. Instead of this platform being regraded like this, we know that these low points are in fact lower than these points, and therefore they're closer to the other contour, so it's going to look more like this. Again, the same logic as that in-class assignment, because although they're all going to have that 3-to-1 ratio or percent, these points are closer to those contours than these ones. So that's why those kind of taper inward. So we have to kind of figure that out as well. So what we can do is take our rotated curve here and find the points on it. So I'm going to go to, again, curve, analysis, and I'm going to use the control polygon. And you'll see now I have points at each corner, which represent your high points and your low points. For this curve to actually work, it's actually drawing 5 points. It's each point of the rectangle, so those 4 points, but then it's also connecting the start point and end point. So there's technically going to be, like this shows, 5 points because it's duplicating one of those points where it's connecting. That's just how the geometry works. So we really don't need that last one. So a way to remove that data from this is that if we go to sets, sequence, col index, or remove an item, I'll drag this into there. And we know we're just getting rid of that 5th point or the index value of 4. So I'm just going to do 4. And so now we truly have 4 points, or the points of each corner. That's just kind of a weird bit of data organization. It doesn't really read as anything, but that's what's going to help with a lot of this. So now that we actually have that kind of cleaned up and have our 4 points, we need to find their z value, or where that elevation is of each one of these points. I can go over to vector and deconstruct these points. And get a panel. And now I can see all the elevation points for these. You can see that the two high points on those ends as well as those low points. So here's something to help make sure that your script works well. If I were to regrade it as is, what do you think is going to happen? What can you see with those point values? Is there a contour, a whole number contour between these points?
Oh, yeah.
Yeah, so this is going to go back to what I was saying before, where if you were to keep it at this point, then you're going to have a contour go through your platform, which is too much of a pain in the ass. So what you can do is make sure in Rhino that you drop it down so that these points are in between a whole number, so that it's somewhere between like 13.9 and 13.1. So I'm just going to drop this down so that all the points, so there we go. I just happened to do it perfectly for once. So now you can see the high points are 13.9, the low points are 13.1. That way we know that there's no whole number contours going between or going through this platform, which is good. Okay. Is that? No, there's definitely. Okay, so the next part of this, let's make sure I've covered. Oh, so right now we have to actually taper the curve around it. So now we have to create that first curve that's bounding this. So this is where we use, again, that same type of logic where we're going to maintain that 3-to-1 ratio. However, we can see that instead of it being a nice, beautiful, let me move that out of the way so I can actually see it. So we have a distance and elevation. We're just going to say like, okay, what's the distance and elevation between 13.915326 and 13.169 something? Oh, what's going on with that? Maybe I'm just zoomed into it. So again, we have to maintain that 3-to-1 ratio. But our numbers aren't that clean. So we see that the distance between 13.915 is, in this case, it's 0.9, I'll just round up to 0.92. And the bottom one is 0.16. So what we have to do is figure out how far to move out those curves. So if it's a 3-to-1 ratio, that means it's just going to be 0.92 of 3. So 0.92 times 3, this one becomes 0.16 times 3. That's what's going to give us that same 3-to-1 ratio. Does everyone kind of follow that understanding? So that's how we get that tapered shape, because we aren't having to actually move out 3 feet because we aren't going in an elevation change of 1. It's really 0.92 and 0.16. Is that clear, or is that just? Okay. So let's go through that now. So here's where we get into a little bit of computer language. I had to actually look this up to figure it out. In order to, again, make this kind of parametric, so that if we ever change the elevation, we need all the information to change with us. So I could just say, what's the difference between 13 and all these values? But if I change the height of this, then I have to manually change whatever that whole number is, which is going to be a pain in the ass. So what you actually can do is use this bit of computer language. So in order to tell these numbers to round up or round down, we have to create a function. So I'll go to math, script, and I'm going to use an expression. So it's kind of a funny expression on how you use this. We only need this one value, and don't worry when it turns red. To actually round down these numbers, so we want to round them down to what? 13. So the way like this computer language works is that it's kind of cool because it kind of fits within the profession, but you type floor and do X. So this is going to round down these values. So now you'll see, now all those values get converted to 3. I don't want to get too far ahead of myself, but we're going to have to do this later. How do you think we round up? Ceiling, right? So you have a floor to round down, you have a ceiling to round up. It's not that creative, but it's kind of funny and cool. So now if I type ceiling of those same values, you'll see now they're rounded up to 14. So we'll have to use this one later, so you can kind of set that aside. We'll put this down there somewhere. So again, like I said, we have to find that elevation change so we can subtract from these values, this value. And now you'll see that you get those value differences. Oops. I'm going to plug those in so I don't need this panel. So there's our change in elevation. So that's how far these points are from those next contours. So this is going to tell us that when we multiply this value by 3, it's actually going to tell us how far these contours are going to get regraded out. This goes back to that 3-to-1 ratio. So we're multiplying these difference in elevation by 3 to give us our nice 3-to-1 grade ratio. So we'll multiply this value by 3, and that's never going to change, so it doesn't need to be a number slider. So this is going to tell us that we need to essentially move those points in either direction, 2.7 or 0.5. So this is how we start to kind of get out of the way. Essentially, we're taking these points and moving them out that direction and that distance. Because remember when we were first going over that, this is where we draw that curve using a compass of like whatever that distance is. That's the same logic that we're doing. Instead of using a compass, we're using a very expensive scripting for that. So what this is going to do is it's going to tell us move these points, so these top ones out 2.75 feet, and then move these ones out 0.5 feet. So in order to actually do that is we have to first, again, it's easy for us to say like, yeah, just move them out that distance, but it also needs to know a direction, which is kind of a pain because we have to include that too. So we're going to find the center point of this curve by doing area. That's going to tell us essentially the direction to move these out in either direction. I'm going to go ahead and hide this for now. So we're basically going to find out a vector from this center point and all these 4 outer points. So we already have those right here. So we find that direction by going to vector 2 points. So we're looking again for the direction from this center point to these outside ones. So this is A. And then these 4 points are B, giving us our direction. So this is going to push those out in those direction, but we also need to know how far to push those out in those directions. So let's kind of clean this up a little. You don't need these anymore. That was just to show you what that does. So we have our distance, so that's what this value is, and this is the direction. So now we use the move command. So we're saying move these points. So that's our geometry. And it's also asking for a direction. So right now it defaults to 10 feet in the Z direction, but we need to go out in these directions by this distance. So I'll stay within vector, use amplitude. So this is taking that direction and telling it how far. So this is the length. So you have your vector direction and the distance for each one of those directions. And now when I plug this into here, you can see that the points, so these are the high ones, those go out further versus these ones go out a little shorter. So now we have our new points. Now all we have to do is go to curve, use the polyline, grab that into there and make sure to right click here, set Boolean to true so that actually closes it. And now after all that scripting, we finally have our tapered contour around. Yay. It's unfortunate that you have to go through all that just to find it out, but it makes it pretty valuable because now if you ever want to regrade it to a 4:1 slope, you could just say, okay, now it goes out at a 4:1 ratio or a 5:1 or whatnot. So it'll nicely change whatever that side slope is going to be. Again, you could probably manually do that, but this makes it so it all kind of becomes responsive. Oh, 18 minutes left. When it gives me my prompt, I'll go grab my charger. Okay, so here's the next thing. So now that we have our new regrading from those different points, we have to actually start to move it in both the downward and the upward direction. So the downward's going to give us our fill curves, and the up ones are going to give us our cut curves. So now we can do something a little simpler. Now we're going to offset these curves by those distances. So I'm going to do offset curve. It's asking for a distance. So how far do these need to be offset by?
1 foot.
3 feet. So I can use the same value here. So that's doing it just one time. Let's actually do it by a series of distances. So I'm going to use series. So we can create a, like it says, a series of numbers. We're going to start at 0. So that's fine. And then the step size, that's what's going to give us our 3 value. I'm just going to right click and say set number to 3. And then for your count, again, this is one of those things where we're just going to exaggerate it. So we make sure that we intersect with as many contours as possible. I'm just going to say like 30 for now. And what this is going to do is create all these curves to offset from there. They're all still in the same plane though. And what we need to actually do is actually do it instead of, because right now they're actually sloping down very gradually. This actually needs to be for our original curve. This is really just to kind of figure out those values, but oops, no, we don't. Oops, yeah, no, that's fine. Sorry. We do still use this one. We're just going to put them at their own height and plane later. So don't worry about them sloping. They should be actually flat. Let me go ahead and grab my charger real quick. And pause this so we don't. Okay, so now, like I said, we're going to follow that same logic as the in-class exercise and try and figure out where all these curves that we've offset. So remember when you, in the exercise where you had to draw all those rectangles around your platform, now we're going to shift to the phase of, okay, where are these regraded curves going to intersect with our existing contours to actually change the contour manipulation. So we have to first actually contour our surface. So let's reference that in. I can go ahead and hide this now. And we are going to contour it. And really, you don't have to change much. You want it to start at 0, 0, so they're all whole numbers. Direction, Z, that's good. And distance, we're just going to do it with our 1 foot contours. So now we can start to see how these are beginning to intersect with each other. So the first logic we need to tell Grasshopper is figure out, okay, which contours are below our platform and which contours are above our platform to separate our cut and fill values. So in order to do that, again, we're going to use a little bit of dispatching logic and Z values to figure that out. We already have, really doesn't matter. We can use this Z value. Let's actually use, again, it shouldn't matter that much. Yeah, let's just use this one all the way back towards the end, our origin point. Or we can even use the centroid point. Well, let's use this one. So we're again going to deconstruct that point to find its Z value. I'm going to shift a bunch of this down. So we have our Z value of 13.915. And now we're trying to figure out, okay, which contours are below that Z value and which ones are above that Z value. So we're going to, again, round that up to, no, I don't think we have to actually round it. So first thing we have to do is find out the elevation of all those contours. So I'm going to go to curve, analysis, and do point on curve. So this is just to figure out where the elevation is of all these contours. You can go ahead and flatten that. And we're going to do the same thing where we're going to deconstruct these points to find out their Z value. And we can see that they're all nice whole numbers in either direction. And so this is where we actually separate the contours. So we're going to go to math and let's do the cut first. So I'm going to do operations and choose smaller than. So whichever contours have a Z value lower than our platform is going to be considered cut. And then we'll do the same thing for the other ones by using a larger than. So it's looking for that first number, which is our platform number. And now it's looking for all of these ones. And so this is going to tell us which contours are below and which ones aren't. So I'll go back to sets, list, dispatch. This is what actually sorts this all out. And so I'm going to use my contours to look at to dispatch. And I'm going to use anything that is smaller than that value. It's not going to change anything because it shows it all. I'm going to use a curve and you can see here are all, now I can see, let's turn this off. I can turn off this. And based off of logic, that doesn't... Oh, wrong. No, that's right. Did I use the right one? Oh, so this is smaller than, right? That doesn't seem right. See what happens. That seems right. Okay, so I don't know why that's A. Oh, if A is less than, sorry. Let's do, I mean, that works. I don't really like that though. So now you can see all those contours that are below that platform are highlighted. Oops, I don't know what that just did. And if I do one for this set, here's all the contours that are above that. So that's how we sort them out. I'm going to turn this one off for now. And so we have those contours that are below it. Now we have to figure out which of those ones are actually intersecting with these ones. And this is where it gets a little tricky. So let's do it like this. So where I gotta refresh my memory. Yeah, that one. Okay. Okay. That's right. Okay. So let's go back to this one. So we need to have these descending in those one value intervals. So let's take those and project them down to a plane. And each one of these, that's weird, I don't know why it does. Each one of these essentially needs to go down one step incrementally. So instead of them all being on that same plane, we need them to go down. So this first curve is going to go down to 13 feet. This one's going to go down to 12 feet and 11 and 10 and in that same order. So this is where we're going to, again, use our floor expression so we know where to start that first one at. So we can see that that goes down to 13. I'm going to use the series component again to say, instead of start at 0, start that value at 13. Then the next one, we need these to go into step size of, because they're going down, it can't be a positive number, it needs to be a negative number. So let's do -1. And the count, again, can be the same value as this. And this is going to be our point that it projects down to. So we'll create a point with these being their z values and plug that into our projection plane. And now you can see that it starts to kind of look like this pyramid. So each one is incrementally scaling out as well as dropping down to each relative plane. So you can start to kind of see what that fill is going to look like based off of this. Now we just have to actually physically intersect them and trim it up. Is everyone starting to see that, how it works? All right. Sorry, I had to actually come up with a script just the other week, so haven't memorized this one quite yet. So like I said, we're gonna figure out which one of these curves or these contours is intersecting with this one. And turn off that. So we're gonna go to intersect, physical, multiple curves. For that, I'm gonna go to sets, tree, merge. So we're just gonna merge all these points or all these curves together, and that'll tell us where those intersections are occurring. I can't remember if I flatten that or not. Okay, so we'll flatten that. So instead of it being this dashed line, we're gonna flatten this. Oops, not graphed. So now you can actually see, let's turn off almost everything. So here's where they're actually starting to intersect with that curve. So these are what those points are creating. And this is, again, where you kind of see from the last class, these are those intersection points that you start to draw from. Oh, but what's good that this does is that it actually tells us, okay, which curves are, or which contours are being intersected with. You can see that these are still considered below that platform, but they're not being intersected with. And that's what this is telling us, is that those index of contours are. Some are duplicated and some aren't. And so we have to kind of clean that up, which is easy. We can go ahead and use this component that says delete consecutives so that we just get rid of any overlapping ones. So now they're just all the single values. And now we say, okay, just choose those contours. So instead of all these that are being pulled in, only focus on the contours that are being intersected with. So I'll use list item. So use these curves. And this is giving us our index. And now we can see that, now we can see that we've even filtered down our contours to this more finer list. And so now we can actually physically replace or cut through them. So we're going to go back to intersect, physical, and do curve and curve. So we have our tapered curves and our curves that are actually being intersected with. You'll see that they should be the same number. There's 30 or no, actually they won't, but anyways. Now I'll select this, so our contours and our bounding curves. And you're also for this. Huh. That's weird. Maybe it's too high or something. So you can see that they are actually projecting down, but my bad, guys. Oh, I think I'm going to try one more thing. I think this is what I forgot. Oh, there we go. Okay, so my apologies again. So in terms of the actual data, these contours are getting cut in the upward direction. So it's saying like, here's like from the bottom, you have your 0 contour or whatever, and you're building up. But the data for this is actually going in the downward direction. So in terms of it understanding the data intersecting with each other, if they're going in the opposite directions, it's going to say that nothing's intersecting. So that's why we have to reverse one of these directions so that they're both going in the same direction. Is that completely foreign language to you guys, or does it make some sense? So imagine like the data for these extensions are going down, but then the contour data is going up. So that's why it says there's no intersection, but you can see now after reversing it that they are creating those intersection points. So you'll have to, luckily when you do the actual cut volumes, they'll both be going in the upward direction, so you don't have to worry about reversing it. So I promise we're getting there. I'll just probably get to the point of only showing you this, but like I said, you can just copy this part and apply it to the other contours, or I could just go over that the next lab because I'm sure it's going to still be troubling. So here's what's great, I promise. Now we can actually split these curves and merge them together. And so we have our parameters for our A curve, which is our existing contours, and the parameters for our B curve, which are our new proposed contours. So we're going to shatter both of those curves at those points. So I'm going to take my contours, and you can see there's this lowercase t for the parameters. That's this one. I'm going to also graft that. Then I'm going to do the same thing with the B parameters of my proposed contours. Let's go ahead and turn this stuff off. So it's still the same thing. So you can see now it's been kind of, again, filtered down, but now we have to actually kind of program it to physically remove that excess. So for these proposed contours, we're essentially getting rid of this part and we're keeping this. And then for those existing contours, we're getting rid of that inside so that they bleed together. And so now you'll see that it does fracture them in different areas. It's just a matter of finding out which ones are which. So I'm going to go to Sets, List Item, and I can see that let's see. So there's that one. So it doesn't seem like this one liked those. It's still kind of overextending, which isn't what it should be doing. Huh. Oh, it's because I didn't reverse this as well. Sorry. There we go. So make sure that that's your new one. So we want to keep that. This is again like so. These curves, these contours, some of them have been fractured into 3 pieces. It gets cut there and there. So there's this part of the contour, there's this part of the contour, and this part of the contour. So for the most part, these contours get shattered into 3 pieces. So you can see that when I hover over this, there's this number 3, which says those are the 3 pieces. But we really need to get rid of that inside value or index item 1. So I'm going to do col index and use 1. So now you can see if I turn this off that those have been trimmed away. And vice versa, these contours have been fractured into 2 parts. So there's the ones on the inside and the ones on the outside. And you can see when you hover over that, there's 2 items. So this is saying, this is highlighting those ones on the outside, but we actually need the other ones. So that's also going to follow that same index logic. So I'll turn this, and now you can see they're actually matching. Now all you have to do is go to curve, join curves, let's so that has 4 items, that has 5, so we'll graph those again. And there you go. Yay, all that for simple cut. But what's cool, like I said, like when you start to shift this around, it's just gonna regrade it no matter what. That's all, folks.